All right. Thanks, Avi. Thanks for having me give the talk, and thanks for having us at the IAS this semester. It's really been amazing. So yeah, this is going to be about proof complexity. This is joint work with my advisor, Toni Pitassi, at University of Toronto, and Hao Wei, who's a new graduate student at CMU. OK. So proof complexity, as per the name, it studies proofs. And here's a kind of overused example of a proof that it's a snippet from the Principia Mathematica. And some interesting things about this are that the tautology we want to prove is 1 + 1 = 2. And
that's one of 100 pages, right?
Yeah, it's 64, I think. 64 pages, uses ZFC. We've gotten it down from 64 pages since then, but it suggests the natural question, which is, if you have a proof system, P, and you've got a tautology tau, how long is the shortest P proof of tau? So this is a question we study a lot in proof complexity and that we understand pretty well. And then another question, a more algorithmic question that would come out of this is, can we actually find short P proofs of tau? And we're going to focus on this one today. But first, just I'm going to go over some proof complexity stuff. So propositional proof systems were introduced by Cook and Reckhow a long time ago, longer than I remember. And we're going to define them as an onto map from proofs to tautologies. And we require that it's checkable in polynomial time. So you can, given a proof in a proof system, you can check that it's actually a proof of some tautology. And we're actually going to make a slight change here. Instead of proving tautologies, we're going to refute unsatisfiable formulas for reasons that may or may not become clear later. And
It's equivalent.
yeah, it is equivalent. Yeah, instead of proving a tautology, you'll just disprove its negation. So we're going to say that a propositional proof system is polynomially bounded if we're going to restrict ourselves to looking at k-CNFs, where the width of the clauses k is not more than log n, so not something too big, and that we're going to have a polynomial number of clauses. And we're going to say that the proof system is polynomially bounded if for all such tau there exists a p proof of size at most polynomial in the size of the tautology, which is n. OK? And since we are refuting unsatisfiable formulas using polynomial size proofs, this kind of looks like a co-NP witness, or an NP witness to co-NP problems. And indeed, it turns out that NP is equal to co-NP if and only if there exists a polynomially bounded propositional proof system. This isn't too hard to show. OK, I want to quickly go over resolution, which is probably the most important proof system you'll see today. In resolution, the input is a bunch of clauses. And the rule that we use to derive.
The clauses is the same CNF you are trying to refute.
Yeah, this is the CNF we're trying to refute.
The
So
conjunction of all these clauses.
yeah, we've got the and of all these clauses, which we called axioms. And we're going to refute them by resolving them. And what the resolution rule says is, let's take here, for example, we've got not D and, or B. And then we've got not A or D. And so from these two, it's a sound inference that we have not A or B. To see this, just set D to cover the other one, whichever one isn't true. And we work our way up, and we eventually derive the empty clause. And if we can derive the empty clause via sound inferences, then this shows that the original thing was unsatisfiable. Now, in this case, notice that the underlying graph is a tree. So we call this tree-like resolution. In general, it doesn't have to be a tree. It can be a DAG, for example. When we're doing tree-like, we might need to reuse clauses like the not B you see here at the bottom. Some other properties of this, size 11 nodes in the tree. Width 3, that input clause has width 3. This is kind of degenerate because the input clause has the biggest width, but sometimes, usually it'll be within the tree itself, and within the DAG itself. And this will be an interesting quantity to us.
So just summarizing this proof system, just all the lines in this proof are clauses, like the
Exactly. All the lines are clauses. The inference rule takes two lines and resolves them. And yeah, you can define a proof system by what the lines look like and what the inference rules look like in general.
It is sound and complete.
It is sound and complete, yes. Also note that in the case of tree-like, this is actually equivalent to solving a search problem. And the search problem being, we know that the tautology is unsatisfiable. Given an assignment to the variables, find the clause that's falsified. So for example, at the top, I would query A. And if it's not A, I'd go to the left. Then I'd query B, say go to the right, because they say that if B is true, then the clause not B is, of course, falsified. And going down the tree, for example, down here, if you assigned A to 0, B to 0, and C to 0, then A or B or C would be falsified. Anyway, this search problem is going to become relevant later. And this is equivalent. Tree-like resolution proofs are exactly equivalent to the search problem as long as you label a leaf with a falsified clause as soon as you can. Decision tree, sorry. Yeah. OK, and just to give you this quick picture, we're not going to deal with most of these proof systems today, but there's resolution and tree resolution. There's the algebraic systems like null-Silensatz and polynomial calculus. So these deal with equalities. We've got a bunch of polynomials that equal 0, and the final line is 1. 1 equals 0. And then you've got semi-algebraic systems like Shirali-Adams and sum of squares, which deal with inequalities. And the last line is -1 is greater than or equal to 0. And this red line here is basically where we know lower bounds, exponential lower bounds. So above that, the proof systems get too strong, and we don't exactly know how to say very much. But below this, we've got a decent hold on things. We're only going to deal with tree res, null-Silensatz, calculus, Shirali-Adams, and SOS, and mostly just these two for today. All right, now we get to the actual problem that we care about. So automatizability was introduced in Bonnet, Pitassi, and Raz, and the idea is that a proof system P is automatizable if there's an algorithm that takes these unsatisfiable CNFs and can return a P proof in time polynomial in n, the number of variables, and s, the size of the shortest P proof of tau. And of course, we have to include the n and the s because we've got exponential lower bounds on a lot of tautologies. So we can't just say polynomial in n.
You need to print the proof, so
right.
Well,
yeah. Although
the time to find it will be at least its length.
Right. That's also true. Yeah. We'll also extend this, of course. So regular automatizability is just for polynomial time. We can also say f automatizability is time, some function of n and s. All right. And for applications of automatizability, so first off, tree-like resolution and resolution are the basis of SAT solvers. So the DPLL paper, David Putnam, Longham, and Loveland, shows that kind of in the way that we did this search problem, you can also design a SAT solver based on tree-like resolution. And then later it turned out that if we augmented our SAT solvers with restarts and conflict-driven clause learning, then we can exactly capture resolution. So automatizability for resolution gives us a lot of information and insight on SAT solving. For PAC learning, there is this connection that was shown in Oleknovich, Braverman, Feldman, Kleibens, and Pitassi. And recently, there's been a lot of stuff on agnostic learning, specifically by Pravesh, who's not here to criticize me, and Livni. And for unsupervised learning, there was...
Why is it related? Algorithm for PAC learning, you didn't explain why they are related to automatizability.
Sorry. So, for example, in the Kothari-Livni paper, I believe that they show that you can get algorithms for PAC learning from sum of squares based algorithms. Which one? The Kothari-Livni? This is a newer paper, actually. So this is about agnostic learning?
Salil Vadan is the
Yeah, I don't think that's...
Oh, OK. Sorry.
That shows the Figos cycle. It shows the connection between...
Figos?
I think you don't want that reference.
OK.
The other Kothari papers. But the bottom reference, it kind of shows that automatizability follow the fence linear.
Yeah, this is the main one, I think.
It just shows that automatizability upper bounds are similar to.
Just say,
Yeah.
louder.
Oh, no, go for it.
Just the upper bounds, like for DNF path learning,
Yeah.
the best proper one is the same as the best upper bound for automatizability resolution, and same thing for tree-like resolution and decision tree.
If you have, so what's the direction? If you have a path
There's
learning.
no direction, it's just that it's the
A
same.
similarity.
Similarity, okay. Analogy, okay.
Yeah, analogy. Although, and then there's this this BGL paper, which is actually talking about optimizing random polynomials over the unit circle, which apparently has found a lot of sum of squares algorithms to do this. And approximation algorithms is also sum of squares algorithms, but sum of squares automatizability. Automatizing the proof system sum of squares is very much related to algorithms for the sum of squares technique, which gives us a lot of the best known approximation algorithms for NP-hard problems that we know. Okay, so what do we know about automatizability? So the first thing is that if you have any polynomially bounded propositional proof system, then as long as NP is not in p-poly, that system is not polynomially automatizable. And this is a connection. This is kind of in two parts, because the intermediate is this thing called feasible interpolation, which I'm not going to go into. But anyway, this is Itai, and then Impagliazzo.
You can say exactly what.
It's an easy proof.
Yeah.
Yeah, okay, so right. If you're polynomially bounded, then you don't have this property called feasible interpolation.
No, I think you don't need that.
You don't need.
You don't need that? Oh, is this direct?
If you have a polynomial bounded proof system, then there exists a short proof for every tautology.
Mm-hmm.
Right?
Yep.
And if it's automatizable, then you can also find this short proof. So you can solve a
That's a good
problem in polynomial time.
Okay, that's a great point.
Size.
Okay, yes. Right, I was thinking of the intermediate connection, but that's actually a good point. It is very direct. Okay, good. Another result that holds for general proof systems, actually this holds for any propositional proof system, it's that approximating the size of the shortest proof to within a almost linear factor is NP-hard. This is a like image.
No, it's
Almost any, yes. Yes, almost any.
Almost anyone.
like any proof system, like Frege, extended Frege, all that.
Anyone we know of right now, right?
But yeah, it may be, the result may possibly could be much stronger. There's no reason linear would be a bound. Maybe within you cannot approximate it to a polynomial, right?
I think it would be surprising if it was NP-hard because of the fact that, some of them have upper bounds.
Yeah, n to the log n or something, or n to the log s.
Why would it be surprising if you could prove that it's hard to approximate by a factor n squared?
For tree resolution?
This is n squared. Yep.
Yeah.
So I'm curious, from the automatizability of a proof system, why would you only get a non-uniform conclusion?
If you define it's non-uniform.
Oh, well,
Yeah.
So it's just a matter of definition.
Yeah.
Okay, thank you.
I guess you're right, N
But,
squared.
why?
Yeah, poly n, I don't think.
I don't think that, yeah.
But
I'm still suspicious, but anyways, I don't know.
well, it would take a pretty new technique, first of all, right?
It's hard, but whether it's NP-hard is different. I don't know what counters
Okay.
Yeah, I don't have much to add there. So now, in contrast to the picture, oh yeah, go for it.
So the proof is just about how many clauses you need to make the thing unsatisfying.
Yeah.
It's nothing really about the proof. But certainly the technique is.
Right. Well, the technique is kind of just stringing together, forcing you to go down this long chain of inferences, right?
It's really just setting up the
Yeah.
tautologies, this minimum circuit.
Monotone minimum circuit satisfying.
The inputs lines.
Minimum monotone circuit satisfying assignment.
And you do a little bit of gadget work to make it
Yeah.
as big as you can and use PCP. But it's not about the proof. It's just
Right.
about minimum unsatisfied.
Yeah, but it's definitely worth noting. So now getting to specific proof systems, in contrast to that picture where we had the red line below which we knew exponential lower bounds and above which we knew absolutely nothing, we actually do have lower bounds against very strong systems like Frege and extended Frege for automatizability under cryptographic assumptions. And we'll see the exact assumptions in a couple of slides, but yeah,
So we don't
these aren't
expect-
polynomially.
Yeah, but they're consistent, right? We don't expect automatizability
No.
response to proof systems.
No, and that makes sense, right? The fact, I mean, we humans can't really find good Frege proofs. I don't know if computers could do it either. This is not, yeah. It's still a great
I
result.
think the easiest way to see it is like, take any like one, if you believe in one-way permutations,
Yeah,
you can just write a statement that says,
yeah. So like, Krychek-Pudlak is, yeah, like discrete log isn't in p-poly. These are like very well-known
Do
assumptions.
you even need a one-way permutation? Could you just use a one-way function?
you can use a,
Yeah, I think that.
Just, say, pick
It's
one
a little-
where there is an inverse and just say, well, I'm going to prove that there's a premium.
So just
It's not, you somehow disjoint.
All right,
so
okay.
like disjoint,
Okay.
discrete log.
Okay,
Diffie-Hellman.
Okay.
Yeah, Diffie-Hellman, factoring Blum integers, stuff like that. All right. Now, what's going to be important for today's talk is actually going back down to the lower systems. So the first, this is kind of the result where all of today's talk starts, which is the first lower bounds against automatizability for resolution and tree-like resolution. So this is a paper of Olekhovich and Razborov. And this is really important for us because resolution and tree-like resolution are the ones that we invoke when we're talking about SAT solvers, for example. So it's really important to understand the automatizability of these systems. And it got extended a couple years later by Gillespie and Loria to cover null Selensats and polynomial calculus. The core of the proof is the same. You have to adapt the technique to work for these polynomial systems, or these algebraic systems, but it's a kind of a direct follow-up to Olekhovich-Razborov. And what we're going to do is a newer version of these two in the sense that it's been simplified. The tautology and the argument have been simplified. We get stronger lower bounds, so these are all polynomial automatizability. We get pretty close to quasi-polynomial, which we'll see is kind of the right answer. And we cover res, tree res, null sats, polynomial calculus, and also the system res k, which I'm not going to talk about today. And it's also in a regime where we may someday be able to say stuff about cutting planes, but who knows?
So just to clarify for those who don't see, the low bounds against automatizability will always need computational assumptions.
Always.
We don't have.
Right, because if.
There are low bounds for algorithms,
Well,
right? So it's
right. Well, if p equals np and np equals co-np, then we're already, we're already done. So here's going to be our main theorems. I wrote the assumptions up there. We're not going to worry too much about them today, but.
no, I mean, you have to explain them, right?
I'll give a couple lines. So, I mean, exponential time hypothesis is one that is more well studied. So this is just saying that, say, 3-SAT can't be solved in 2 to the little o of n time, or 2 to the n to the epsilon time for epsilon less than 1. And gap ETH is a slightly more recent and slightly stronger assumption.
Yeah, just slower. So
Sure.
at least for people who don't, it's just like a strong version of p different, and then
Yes.
instead of saying there's no
Polytime
polynomial
algorithm.
time algorithm for
For
stability, there's no even exponential time algorithm.
Or
I mean,
sub-exponential time.
algorithm.
Exactly. Yeah.
So these are the assumptions that will be
Right.
behind the.
Right. And actually, I should.
They are somewhat different than the Algorithmic.
I should mention, yes. So Olekhovich, Razborov, and Gillespie, Loria both use the same assumption, and it's a very weak assumption from parameterized complexity. We'll see it in a couple of slides, but the assumption says that WP, which is this class that encompasses basically every fixed parameter-based algorithm you can imagine, is fixed parameter tractable. So it can be solved in time polynomial times some function of just the parameter. I don't want to go too deep into parameterized complexity, but suffice it to say it implies ETH. It implies the exponential time hypothesis and more. So
Do we know that resolution is like n to the log s automatizable or something?
We do, and we will get to that.
All right. So basically what you're saying is that known automatizability of resolution, you can't improve it by too much, assuming the ETH.
Exactly.
All right, thank you.
Yeah, no problem.
Oh, right,
Yeah.
right, okay. And by the way, you know, the reason like gap ETH is stronger than ETH is just that if you use the PCP theorem, there's like a superlinear blowup.
Yeah.
Is that the only reason? Okay.
Yeah.
All right, thank you.
Yeah, and just to clarify, so the ETH assumption, again, this is, we can't solve SAT in sub-exponential time. Gap ETH is saying now you have to distinguish between satisfying CNFs and CNFs which are not even close to satisfiable. And you have to do that in sub-exponential time. The number of clauses you can satisfy, the maximum number of clauses you can satisfy under any assignment.
So these are weaker, even the second theorem is weaker than Algorithmic.
It is. No, yeah, well, okay, yeah. So I should say that, yeah, we started this work actually to standardize the assumption because we didn't know a lot about parameterized complexity, and we wanted to do something like exponential time hypothesis, which everyone knows. So the trade-off is that, yes, our assumption is technically less plausible. I think people still believe the ETH. Gap ETH is pretty new, so we'll see how that goes. But
the consequence to the automatizability low bound, you said local to the 1/7 or something.
Yes, exactly.
So, and in their results, it's just low, right?
No, they don't get anything.
No, they only get super polynomial.
They get only super.
Yeah.
So it's stronger than
That's what
theirs.
I'm saying.
Yes, our result, yes, the actual lower bound is stronger.
And we think that we can change ETH to theirs, it's just, we didn't want to because it's ugly.
Yeah,
I will not.
if you regress back to, or if you go back to their assumption, the parameterized complexity assumption, you should be able to recapture the same argument, basically. Yes, it's important to note that because they're working in parameterized complexity, it's almost inevitable that they can't really beat super polynomial. Just, no polynomial automatizability. We can talk offline about that a bit more. So we're going to focus on the top one today because the proofs are pretty much identical, but the ETH version has a lot more really ugly parameters. So to streamline things, we're just going to do the gap ETH one today. You'll see in a couple slides that there's only one thing that changes, and it's not really the key of the argument.
But I don't know if gap ETH is a stronger assumption.
Yes, it is a stronger assumption.
It's a stronger assumption, and you get a lower bound which is weaker.
Which is stronger.
Log S versus log to the 1/7.
Log S.
Yeah.
Oh, there's another.
There is another log.
Oh, sorry.
Yeah, sorry. Oh yeah, no,
sorry, yeah, good.
we still have one log to knock off in theory, which we'll see in a couple slides. But actually, the state of these exponents completely depends on some problem from ETH or gap ETH. So if you can improve that problem, it's not a matter of improving the proof complexity argument at this point, actually. All right, so this is just summarizing all the results I just talked about. Here are the assumptions if you care about them. And yeah. OK, so now I have to take a detour because there is another notion of automatizability for which we know quite a bit. So the first thing is that if tau has a width d tree resolution or resolution refutation, you can actually find it in time n to the O of d. And the way you do this is you literally just take every clause you currently have, you resolve all pairs of them, and save those clauses, and then keep doing this. Make sure that you never cross the threshold of width d, and make sure that you don't derive anything you've already derived. And at some point, the empty clause is going to pop up, and that's going to be it. So I wanted to put this in as a theorem citing Toni, but she insisted that this is obvious. So slightly more interesting is that there's this Edmonds and Pagliazzo paper that talks about a lot about nullsots in PC, and one of the things they show is that a Grubner-based algorithm can do the same thing. So if you have a degree d nullsots or PC refutation, you can find it in time n to the O of d. And then, because Shirley-Adams and SOS are linear and semi-definite programming respectively, you can do the same thing for them using linear hierarchies or semi-definite hierarchies. So this top one is just all of those put together. We also know that it's tight. I don't know about SOS. I don't know if this is tight for SOS, but for all other proof systems, we have examples which have width or degree d, and for the size of the shortest proof is like n to the d. So you won't be able to improve the width-based automatizing algorithm. And what's worth noting about this is that the size might not be n to the d. It might be a lot less. So this doesn't, these two slides don't mean that automatizability is pretty much solved. There could be a huge gap between the amount of time it takes to find the proof and the actual size of the smallest proof. So
but these are lower bounds of the size of the smallest proof.
these are lower.
The
These ones,
middle one, yeah.
yeah, these ones are just showing that this algorithm is tight. You won't be able to
The
improve.
algorithm is tight. It's just that
It-
the proof may be as long as the time.
Right, the proof-
But the time is not as a function. It's not written there as a function.
Right, okay. Yes, okay, thank you. Yes. Okay, good. All right. So, sorry, this first one's one name. This is a function of the dashes.
This one tells.
Yes, Ben-Sasson and Viggerson. So this is a result that we use a lot in proof complexity to get lower bounds. And it's that in tree res, the width is at most the log of the size. And for resolution, the width is at most square root like n log s. And why am I bringing this up now? Because if you actually just take the algorithm that we had in the last slide and substitute in log s, you immediately get what Scott was saying, which is that tree res is n to the log s automatizability. And you can actually prove this a lot more directly than using Ben-Sasson and Viggerson. It's just a recursive argument. But I just wanted to show that you get it directly from here. And res, likewise, is n to the square root n log s automatizable. Now, so this first one suggests that our result is getting close to where we can't say anything more, because we won't be able to get a lower bound.
Wait, you're saying once you upper bound the width of the proof, then you can just do a brute force search?
Yeah, exactly.
Okay,
Yeah.
thank you.
Yeah. So for resolution, who knows? We might have a lot more to say, because this is like a sub-exponential lower bound, so there, or upper bound, so there may be a lower bound of sub-exponential automatizability. But anyway, null sauce, it turns out it's also n to the log s automatizable, and I don't think there are any other upper bounds that are known for automatizability. So, okay, so now let's get to how we're actually going to do today's result. So if you want to get an automatizability lower bound, there's something that pretty much all of the ones thus far have done, which is you start with a gap problem. You do some magic and turn it into a tautology such that the yes instances have small proofs, and the no instances have no small proofs. And in particular, you have to do this without actually solving the problem. So you have to do this in some way such that the gap in the original problem carries over to this tautology. And then once you do that, you get your lower bound by just running the theoretical automatizing algorithm you have, and then just checking how long the output is. Yeah, you run it for a small amount of time, smaller than whatever the lower bound on this proof size is. And so, of course, the better you can get your gap, and the harder you think your problem is, the better of a result you get in step 3.
So again, the step 3, you assume that you have a polynomial time.
Yeah.
Let's say, automatizability algorithm.
Right, and now you
run it on the tautology.
the tautology tau that comes out of your step 2, and then you cap the runtime of it.
Let's say for polynomial time.
Yeah. And so, for example, if you don't have polynomial-sized proofs in the no instances, then you run your automatizing algorithm for polynomial time.
So all you're using is the fact that the length is
The length of the shortest proof has a gap.
But the length of the shortest proof is a lower bound on the time of the algorithm.
Exactly.
That's all you're using.
Exactly.
It's not a lower bound on. It's not really a lower bound on the time. It's just a lower bound.
Right.
And algorithm just says that the time run by any automatizability algorithm
Is at least
the
length of the
proof,
shortest
and you're
proof.
using
Exactly. But you also need to use the fact that you might run the automatizing algorithm runs for time polynomial or quasi-polynomial in the size of the shortest proof. In the yes instance, that means that you might take a lot longer than the size of the small proof that you get, that this thing has. So then you need to make sure that whatever the runtime of the automatizability algorithm is as a function of n and the size of the shortest proof, when you plug in the upper bound you get here, it still is smaller than the size of the shortest proof in the no instance. Because otherwise, at the end, you wouldn't be able to tell what happened.
So the gap between the two has to be, you know, like if you want to
Sufficiently
have
big.
a polynomial gap, then you say the yes instance maybe has size n proofs, and the no instance say has no polynomial size proofs. So then you can run it for time
N to the
polynomial
10,
n.
Yeah, n to the 10. Right. Yeah. We'll see exactly how this plays into our problem in just a second, but thanks. All right, so first we have to pick our gap problem, and here's the only time you're going to see the assumptions, gap, ETH, and ETH. So the gap hitting set problem, I'm going to streamline the parameters because we don't need too many of them for this problem. So the hitting set instance is going to be a universe of size n, and there are going to be n sets over this universe. And a hitting set for this instance is any set of elements in 1 to n that intersects all of the sets in the hitting set instance. Oh, yeah, so we're having n sets and universe of size n. Usually you see it differently, but we're just going to keep it as one parameter. And now we're going to call gamma the size of the smallest hitting set. So in this case, this is the smallest hitting set, I believe. So I outlined it in green. And the gap hitting set problem, again, streamlining parameters a little bit, is that given an instance of n sets over n, distinguish whether the size of your smallest hitting set is at most k or is at least k squared.
So this, the existence of this follows from ETH.
The existence of...
Such an instance. So such that this is an exponentially hard problem.
Yes, yes, yes. So I didn't put the ETH assumption here, but the gap ETH one says that if you assume gap ETH, then this problem can't be solved in time n to the little o of k. Obviously, it can be solved in time n to the o of k, because you can just check for a hitting set of size k. And this holds for k up to about log n. I'm suppressing some factors there between log and log. So nothing big. And this is, you may note that this is somewhat similar to the exponent that we get in our hardness result. And it turns out that for ETH, this optimal value of k is like log to the 1/7 minus little o of 1, log n.
Okay, but potentially it could go up to log n.
It could go up to little o of log n. Yeah, the only so we know an approximation algorithm for hitting set of size of up to log n times the optimal. This is like a greedy algorithm, but we don't know. So for, I think, just the regular hitting set problem, you can't do better than log n, right? I think Figa showed that.
Yeah,
But we
so
do.
that's interesting that it's so
Yeah.
much worse.
Yeah. So these actually come from recent results. So this is Chalmers-Sook et al. This is from 6 months ago or so, and they had a new paper out about 3 days ago. But I didn't put it on the slides because I didn't have time to check the parameters. Say it again?
They're going to get this down.
Yeah, eventually they're going to get this down. And here's the cool thing. From here on out, if you can improve any of those results, you immediately improve everything that we do today.
And
Up to a certain threshold.
Stating it differently is for whatever k you can do this.
You-
Right? For whatever k you get
Yep.
that n to the little ok is not sufficient, you have a lower bound.
Exactly.
On your automatizability.
Exactly. So currently this is the best one. Again, it might go up to log.
And you need really k and k squared or k and k to the 1 plus epsilon will be.
Oh, so what ends up, yeah, so we just did kk squared. The reason why is you're balancing these two things. It turns out that your exponent, the n to the little o of whatever, the lower bound that you get for automatizability, it's the minimum of k and the gap. So if this is k versus hk, then it's the minimum of k and h, which is why we picked,
The gap, okay.
yeah, which is why we picked, kk squared. Yeah. And all of these are actually, these are all fixed parameter based results. All of these results are like from gap ETH to some fixed parameter retractable problem. And so you actually have to do some work. This theorem, as stated, is not in the paper, because you need to actually figure out, once you fix k and k squared, how big of a k you can get. They kind of do the opposite thing, where if you pick a gap that's huge, they pick a k that's small. So
Again, in Algorithmic, which was borrowed, they also use the same gap hitting
they used
hitting set, sorry,
no, they used minimum monotone circuit satisfying assignment.
which is not the same, basically.
Well, yeah, this is just a special case of it, essentially.
It was a real pain because their problem has way more variables because it's a whole circuit.
Yeah, actually, this is going to make the tautology a lot easier, just having this. And this is why we can basically recover their result if you want to work under a different assumption. It's just that if they're working under a fixed parameter assumption, then you can't fix the parameter k to be the best one you want, which is why you can't get a super polynomial. OK, so now step 2. Again, this is where all the magic happens. So I'm just going to say that here's going to be our main technical lemma that we're going to prove for the rest of the talk. The rest of the talk in a minute. So if you have k like log n, you can, of course, make this better. But for now, let's say k log n. Then we can map hitting set instances to tautologies in such a way that if the size of your hitting set is at most k, then the size of the shortest proof is at most polynomial in n. And if the size of the hitting set is at least k squared, then the size of the smallest proof is n to the k. And so, Avi, what you were saying, yeah, if this was like h times k, then this would be an h up here instead of a k. Yeah. All right. And this works for all the proof systems that we listed. Say it again? Oh, for res k, there's a slightly different trade-off, actually. That's a different k. So for, yeah, I'll get back to that at the end, maybe, if we've got time. All right. So now let's just see how 3 works. We basically talked about it earlier. Sorry, this slide's going to jerk around a little bit. I couldn't get this to work out. All right, so we're going to pretend we have an automatizing algorithm running in time n to the little of log s.
You're not showing the tautology concept?
Oh, yes, sorry. This is going to be the rest of the paper, so or the rest of the presentation. So I'm just going to quickly go over why this already implies it, just going through the details. All right, so what do? Take your gap instance, turn it into a tautology, run the automatizing algorithm for n to the little o of k steps, and check if you've got a valid output. And so what happens? So in the case where if you're in the good case, then s is n, or s is order n. And so the function is n to the little o of k, because k is log n. And so we are going to get a valid output. So n to the little o of log n is n to the little o of k. So if we run the automatizing algorithm for n to the little o of k steps.
You run it for n to the little of k time. That's really what.
Oh, yeah,
anyway,
time.
Yeah, that's what you do for any k.
Yeah, yeah, exactly.
You run it for n to the little of k time.
Yep. And then you see if you get an output. And you can, like we said, we can check this output in polynomial time. So because it's a propositional proof system. And so now in the bad case, as Avi mentioned, the size of your shortest proof is longer than the amount of time you're running the automatizing algorithm for. So there's no way you're going to get a valid proof, because there's not even a valid proof of size smaller than that time. OK? Good.
So is it necessary to?
Hmm?
I mean, so it's a natural thing to do, to just
Yeah.
find a gap in the length of the proofs. But
Exactly.
Could conceivably an easier thing would just to use the assumption to say that to prove something about the time to find the proof as opposed to. So it's not clear that it seems like first you have a hard work there to show gap in the proof
Are you
line.
talking about the fact that it's really the decision problem instead of the search that we're trying to do?
No. Just that.
So
You get a consequence, a lower bound on the time it takes to do something, right? That's,
yeah.
Right. This the conclusion of your theorem is a lower bound on the running time of some.
Yeah.
To solve some problem. Your assumption is also of this nature. It's a lower bound on the time it takes to find something.
Yeah.
To do something, right? In the middle, you create something which is potentially more difficult, where it is has to do do with the length of the proof of something. Right? So it's not clear that you have to pass in the middle.
No, I think maybe.
Through the proof length. I mean, the proof length may have been short and still hard to find. I'm not, it's not that I know how to do it. It's just that the assumption, the conclusion are about the running time of an algorithm.
I guess.
And in the middle,
sorry.
you are constructing something which is harder, maybe harder to construct than you need.
So, I mean, what would a tautology look like where the proof is short, but you argue that it's hard to find it?
I don't know.
Well, yeah, it seems like it would have to be based off of some hardness assumption, at which point, you know, you're kind of.
Decisions in. So it's like it's a matter of whether you can reduce or if you can ask, is there a proof of this length? And you can ask, is there a proof for this bit is this of this length?
Yeah, so maybe.
Which is what's going on.
Yeah.
But it's not clear to me that in order to prove, let's say, strong automatizability result, you need to prove, you know, a gap in the proof length as opposed to just a gap in the time it takes to find the proof, which is more of the nature of your assumption.
I guess if we're talking past each other, maybe.
Yeah, maybe it doesn't make sense. So, yeah, it's,
Maybe I'm
Yeah, I suspect you end up kind of jumping through the same hoops if you do that.
maybe.
Because-
It would be nice to prove that you have to have such a construct in the middle.
That's true. Well, I'm not saying that you couldn't do it your way. I'm just saying it might end up being, you know, the work that you do might end up being kind of superficially the same work. I don't know. We can talk about this offline. Okay, so I guess the last observation is we, of course, ran in time n to the low of k, and this contradicts gap hitting set, or gap EDH. Good. All right. For the rest of this talk, I wrote this all up here. This top line, don't worry about this bottom line for a second. It's just because we're going to fix this parameter m, which is going to be n to the 1 over k. In particular, k log m equals log n, if you just take logs. This is very important, so I'm going to leave it up here so we can refer back to it where we need to. And there's also this property that for the value of k being fixed to log n, you get that k is at most log m over 4. You are going to see in one slide why we care about this.
But if you care about it, it's not clear how you can use a better k in the...
K can go up with, obeying all three of these, k can go up to square root log n, which is the ceiling for our technique. So it's close. It's not quite there, but yeah, I was going to mention. Thanks. OK. Now we can start to get to that bottom picture. So we're going to fix an object called a universal set, which is just an m by m matrix where if you pick any collection of columns of up to q columns, so we're going to say it's mq universal. If you pick up to, or sorry, q rows, then any column vector is represented in it. So in this case, if we pick an I of size 3, then all 2 to the 3 possibilities of column vectors are available here. And we're going to impose an additional requirement, which isn't in the definition of MQ universal, but that it's symmetric. So if you pick any up to q columns, then all row vectors are represented. So again, if you pick these 3 columns, then all possible row vectors are represented.
So what is symmetric? The matrix?
The matrix isn't symmetric. This universal property is symmetric.
Yeah, so you want it both for rows and columns.
Yeah, we want it for both rows and columns. Usually it's only defined with respect to rows. But if you define it with using something like the adjacency matrix of the Paley graph, which is, I don't want to get into, but that's what Aleknovich-Razborov did, then you do get this symmetric property because it turns out the matrix is actually symmetric. OK, so this is just going to be a gadget matrix that we use. So you can fix this A. M is the M that we defined, and Q is log m over 4.
If you were to pick the matrix at random, could you do better than log n over 4?
Ooh,
No,
I don't think so.
What do you care about the constant? You cannot get this Q bigger than log n.
Right.
Well, log m certainly.
I'm wondering if you could get rid of the square root of these terms.
Oh,
You can get,
that won't help you.
you want 4, what do you want? 2 instead of 4?
I wanted to know if this was all, if one could get to the log n or something.
Yeah, random. Well, not quite log n, but
Quite
very close to 1 log n. Yeah, for random.
Yeah.
Is this the best explicit construction that's known?
going through the paper.
Actually, I'm not sure that Paley graph doesn't give you something close to 2.
Oh, really?
Yeah.
Oh, no, I think there's a, I think they show that there, like there's a book by Alone, Tools of Higher Algebra, and they show that the number of row, if you pick any row vector that you want to appear, it appears m over 2 to the q times minus something like m to the 3/4, or some.
Yeah, but we don't need that strong of a
I don't. Yeah,
But the m to the 3/4 could potentially kill this, kill it off once you get that, or it's like a little low.
But it's not that many.
Yeah, so
okay.
I mean,
I
it's,
don't know why you care about this concept.
yeah, it doesn't, so actually, even if this 4 was gone,
Yeah. No,
Yeah.
I understand that.
even if this 4 was gone, you'd still get that k has to be at most log m, and k log m is equal to log n, so you get that k is at most like square root log n. It's not the 4 that's actually killing us.
Yeah.
Okay. Even though we're in logs, yeah, so sometimes constants kill us.
So it's not related to the two-source extracted property.
I don't believe so.
No, it's a weaker.
Yeah. Okay. So now we're going to show you some pictures, which are going to be our tautology, kind of. So first, I want to explain these two matrices that we're going to implicitly define, m alpha and n beta. They're both going to be n by m matrices. So first, m alpha. For every row, we're going to have a variable that takes a value between 1 and m. So
This is independent of the instance. These matrices depend or don't depend on the instance.
these A matrices? You see?
Clearly
Oh, yeah, no. At this point, we are defining tau sub cal s. So these matrices are going to depend on
this is
the
your
hitting set instance.
Okay, so this is your instance.
Yeah, this is going to be our hitting set instance that we get as input.
Okay, good.
Good. Remember, k is fixed, so m is fixed, n is fixed, etc. This top matrix actually isn't really going to depend on our instance, but so again, each of the n rows is going to get an assignment, some number between 1 and m, and what that number is going to say is go into the matrix A that we just defined and just take that row and put it there. So for example, here the assignment to the first row, alpha 1, is equal to 2. So we go in, we find the second row of A, and we put it in the first row here. So 0, 0, 1, 1, 0, 0, 1, 1. Here it's
So n is the number of vertices in this hypergraph.
number of vertices, yep, and the number of sets. It's both of them.
Also the number of
Yeah, and we're actually going to use that pretty soon. So is the definition of the M matrix clear?
So it's just
You just fill it in.
it's a super, you take your A matrix and you duplicate some rows.
Yeah, you'll have to duplicate a lot of rows because n is a lot bigger than m, but you can make it all the same row if you really wanted to. I wouldn't advise it. So for n beta, this is going to be our second matrix. We're going to define it column by column instead of row by row. And how we're going to define the column is, once again, we're going to have a variable that takes a value from 1 to n. And here, you say beta 1 is equal to 4. You go in, you find the fourth set in our hitting set instance, and you make this thing the characteristic vector of it. So set, S4 has 2, 3, 6, and 7. So we make 2, 3, 6, and 7, 1, and everything else is 0. Beta 2 is 2. This just has 7 and 10. So this is just 1 and 7 and 10 and 0 everywhere else. So this is going to be the implicit definition of these two matrices. Implicit just because we're only defining these alpha and betas. So to make it more formally, if you want to see it in a matrix picture, so consider an n by n matrix, which I drew up here, which is just kind of the...
Take it back.
Sure.
So these are, for every choice of labeling, either the rows here or the columns,
Mm-hmm.
there would be a matrix.
Yeah.
So alpha has to do with so alpha is an assignment. Alpha
Yeah.
is an assignment.
Alpha is an assignment and beta is an assignment.
Yeah, so but alpha is an assignment to n variables from m, right? Alpha is an assignment
Yeah,
to
n variables from m. Actually,
The other one is the opposite.
yeah, m variables from n. And actually how we're going to do it is we're going to have, for each row in m alpha, we're going to have log m binary variables, which you just interpret as a number from 1 to m.
Okay, so that's the encoding, but before that,
That's the encoding.
Given
Yeah,
Given n values from m, you can define the m alpha.
Yeah, m values from n define the n beta. Exactly. It's just picking rows and picking columns. So we're going to have n log m plus m log n variables, because for each of the n rows, we have log m variables. And an assignment to this, of course, defines the alpha I from which we pull our row. And each of the y variables is going to be log n variables from which we can pull our column. OK, good. And so note that then, yeah, so the ith row of m alpha is the the ith row of m alpha is the alpha ith row of A. And the jth column of n beta is the beta jth column of the adjacency matrix. Yeah, if you need to refer back to the adjacency matrix, I put it there. OK. And now, what is the tautology going to state with these variables? And then I'll give the intuition behind this entire rigging up. It says that there's an alpha and a beta, so an assignment to all the rows of m alpha and an assignment to all the columns of n beta, such that there's no ij where they share a 1. All right.
So the ones are disjoint.
The ones are disjoint. And now here's the intuition behind.
This is the tautology.
This is.
Oh,
We'll get to it in a second why this is unsatisfiable, because it is. But here's how you can think of this thing. So let's say I have a definition for m alpha. So I've filled out all the rows of m alpha. OK? Consider the first column of m alpha. So this is a vector of length n. Treat it as a set in our hitting set instance. So for example, here there's a 1, 5, 7, and 10. So 5, 7, 10. Now, ask the question, is this a hitting set? Is it a hitting set? And if not, prove to me that it's not a hitting set. So in this case, 5, 7, 10 isn't a hitting set. The reason why is because set S3 is not hit. So what can we do? Well, if you put set 3 in the first column of n beta, then it's the case that none of their ones are disjoint. No ones overlap. So in other words, you can think of column 1 in n beta as a witness for the fact that the first column in m alpha is not a hitting set. And likewise, we can go and fill out the rest of the columns. And so basically, this tautology says that there's a way to fill out the m alpha matrix such that there are so that none of them are hitting sets. None of the columns in m alpha.
Of course, there's a way.
But they have to be pulled from this matrix. Right, so if I could pick this however I wanted, I'd fill it out with all zeros.
So you have to pick it from there.
You have to pick it from your universal set. But you're allowed to pick whatever rows you want. And then you have to show that it's none of the columns that show up in this matrix are hitting sets as a result. That's what our tautology says.
So again, the tautology, another way of saying the tautology is that one of the columns of A must be.
Right. So this is universally false, and we'll see that in a second. The actual tautology of it would say that no matter how you fill out alpha and beta, one of the columns is a hitting set. One of the columns of alpha is a hitting set. So whatever you put in beta, n beta there, is hit by that alpha. So here are going to be our clauses. It's basically for every I, j, and then assignment to I and j, such that they would both be 1. You get that it's not the case that both xi equals alpha I and yj equals beta j. This thing is just an and of all the xi variables with the right ones negated, such that this thing is 1 if and only if xi gets assigned alpha I.
We don't really need Boolean encoding at this point, right? I mean, eventually you want to.
Yeah, eventually you want it.
Just to think about it, we don't have to.
Intuitively, yeah.
Variables are, yeah.
Exactly.
Think of them as variables from M.
Right. For the moment, right. Just to see how the tautology operates, you can pretend that alpha is just a variable alpha I is just a number in M, and beta j is just a number in N. And this is saying that it's not the case that xi equals alpha I and yj equals beta j. All right. So just to make sure that we're in the regime I promised, the clauses now in the Boolean encoding, This is log m Boolean variables, and this is log n Boolean variables, so the width is like log m plus log n, which is log n. And the number of clauses is, there's n i's, there's m j's, there's 2 to the log n assignments alpha I, and there's 2 to the log m assignments beta j. So this is n squared times m squared clauses. Polynomial. All right, good. So I haven't lied to you. And now we can get to the part where we say that this thing is unsatisfiable as long as the size of the smallest hitting set is at most log m over 4. All right. To say it simply in a picture, let's pretend you filled out, let's pretend you have a smallest hitting set H of size gamma s. And you filled out the M alpha matrix in those rows. This is at most log m over 4 rows from the universal set A. So now go back here. If you have at most log m over 4 rows from the universal set A, then there is a column, any column vector you want to find exists. And in particular, the all ones column exists. And now we already know that the tautology, we've lost, because we've filled out a hitting set with all ones in that column. So just to see exactly how we messed up, move to the n beta matrix and look in the same column. This is a set from the hitting set instance, which means it's hit somewhere, which means it has to have a 1 somewhere in this hitting set, no matter what beta you pick here.
So just a second.
Mm-hmm.
In the M alpha matrix, you need to have, you fill it with rows of A.
Yeah, you fill it with rows of A.
With rows of A. So
Yep.
if you, right.
Yeah. We don't need the symmetric thing just yet, but for now, just this universal property.
It could be in the same row.
Yeah, if you tried to fill out this matrix with the same row everywhere, you're even right,
many ones.
because it's at most log m over 4 rows from the thing. Even if you pick duplicates, you're actually making life easier.
No, you're making life easier to find ones, but not to find all patterns.
Oh yeah. No. Yes.
That's
That's a good point. Yes. Yes. You find all
because
ones.
you're looking for all ones, it doesn't matter if you take duplicates even of one.
Right. Okay. Thank you. Yes. That's actually a very good clarification. But okay, once we found the all ones column, which we know exists once we fill out these rows, it's clear why we've violated this tautology. And just to make it formal, so you've got I1 through I gamma, which is a hitting set. This is at most log m over 4 rows. It's all ones there. I don't actually need to do this. And in particular, for that I and j, alpha I, beta j, there is one of those axioms because it satisfies exactly the property we don't want to. OK, and this actually suggests the upper bound that we need for our main technical lemma.
The argument is sort of,
Yeah. It's actually
you have to be a bit.
yeah. No, you're right. It is important that.
Taken, half of that from one row and half of that from another, but you still find it. Well, you just look at the number of distinct rows you have. It's smaller than
Yes,
this number.
right.
There's a column of ones, and if you replicate them, they'll still be
That thing will still have ones. Yes, exactly. Yeah, it's at most log m over 4 distinct rows, I guess I should say. Yeah. All right, so now this pretty much immediately suggests what upper bound we're going to do. And this is where there's this trapdoor effect, which is what you always need to do, or what we generally need to do when we do this, when we try and get this gap to carry over. So.
Well, which side are you on? I mean, which direction? Where are we? I mean, you just proved that
it's unsatisfiable.
If there is a small hitting set, then it's unsatisfiable.
Right, and that's what we're going to prove. We're going to prove the.
No,
No, I now want to show that there's a short proof of it.
Okay.
I mean, it's pretty direct from what I just said, but we should look at it carefully. So we're going to prove the upper bound in the main technical lemma, which is that if the hitting set size is at most k, then there's a polynomial size proof in all these proof systems. So in general, we're just going to show it for tree res, and since all of our other proof systems polynomially simulate it, we're going to get it. So the only real observation is, again, instead of thinking of tree resolution refutations, we're going to think of decision trees solving the search problem. So you want to find a violated clause. And then it's basically exactly what we just said. each of these columns in the minimum size hitting set has log m Boolean variables. So we're going to query all log m variables for every row that's in the hitting set. Then, once we do that, we know that there's an all ones column. So our decision tree will then query all of the log n Boolean variables in that column for n beta. And from this, we know exactly which clause is falsified. And what's the size of this decision tree? It's at most exponential in the number of variables we queried, which is k. We picked k rows, because gamma is at most k, times log m plus log n.
It's not really exponential number of variables, it's exponential height.
In the height, sorry. Yes, because we actually query different y variables in different parts. Yeah, so it's the height. But the height is the same along all paths. It's k log m plus log n. K log m, as I promised you, is equal to log n. This is n squared.
So the y variables that you query are different.
Yeah, this is different for each setting of this thing. Or it may be different for each setting of x1 through xk. Or, yeah. But you're still only, you query k log m variables, and at the end you're going to query log n variables, whichever log n variables they are. OK.
Can you back up for a minute? So, just wanted to point out that I think you already did, but maybe you should say it again, it might have been too quick for people, about, you know, you have this proof, but you can't, it's hard, the only reason you have it is
Yes. So this is highly non-deterministic, right?
like finding it.
Yeah.
Need to know what
This
the
is-
hitting set is.
Right. So this is why it's kind of a trap door. So we obliviously made this entire tautology. We didn't have to know what the size of the smallest hitting set was, but it turns out that the smallest proof exploits that smallest hitting set, even if we don't know how to find it, which is where all of these arguments come in. That's kind of the trap door that we're talking about. But what we want to show is that this is basically the best you can do. We want to show that you have to know about the smallest hitting set, and you have to know all of the rows in that smallest hitting set. So that's what we're going to do in the lower bound. And to make that easier, I'm just going to make a small change to this tautology. Instead of log m
Bound
on the size, this is going to be in the bad case.
in the best case, where there is no small.
Well, there's no small hitting set. Yep. So now instead of log m variables per xi, we're going to have 6 log m variables and 6 log n variables for yj. And then we're going to have a function f of x and functions f of x and f of y. And f of x just sends 6 log m variables to log m variables, and f of y sends 6 log n variables to log n variables. So if we get an assignment to xi, we just plug it into f of x, we get some number 1 to m out, we continue as normal.
Fx is also part of the input.
F of x is fixed. If f of x is fixed, it's going to be a gadget like this thing. We're going to pull one right out of the book.
Can I interrupt for a second?
Mhm.
So you might be I don't know if you need a break.
What?
Also, I don't know if you need a break.
Oh, actually, that's true. Before we do the lower bound, we can take a break.
You're actually changing the tautology on
Oh, no, I am. Yeah. But actually, this is a good point. We're about to go into the lower bound, which is where the work happens, and it's 11:35. So let's take a 5-minute break.
Okay.
All right. So just again, the upper bound is looking at all the rows of the hitting set. So intuitively, once we pop the size of the hitting set up to k squared, this tautology should become harder to refute. And that's what we're going to get into. But as per our discussion right now, we're going to first blow up the number of variables in each row and each column by a factor of, say, 6. We only picked 6 because it's bigger than 2 times 2.
They also have an error correcting code in their proof, right?
They do. They don't actually put the numbers in there. Their x variables are the same as ours. Their y variables are a little bit different. They error correct code their y variables, and they've got copies of their circuit and whatnot. So I guess our main simplification is cutting that whole circuit out. Yeah, but they use error correcting codes as well, so we're not doing anything surprising. Everyone does. Yeah, it's life becomes a lot more difficult, as we were just discussing, if you don't have these error correcting codes. But anyway.
What do you mean everyone? This no automatizability proof.
No, I mean lower bounds going from size to width.
From what?
Like to get a size of a width.
Yeah.
We always thought,
Right, because that's exactly, I mean, we're proving a lower bound. We're, of course, going to prove a width lower bound, and then we're going to turn that into a size lower bound.
It's different here when using this also to prove the width bound.
Yes, that's true. We actually do use this as a way to prove the width bound, which is pretty important. And that's actually why we pick, so it's important that these functions f of x, which is going to be our mapping, and f of y, have this surjectivity property. I didn't define it here, but it basically says that if, let's take a look at x1. If I fix at most 2 log m bits in x, the function restricted to that assignment is still going to be surjective on all m possibilities, on all m outputs. And likewise for f of y,
So
for 2 log m.
You want to say that looking at 2 log m gives you nothing?
Gives you nothing. And so, and by the way, the reason we picked 2, the first log m is going to be for our width lower bound, and the second log m is going to be for our size lower bound, like our random restriction argument. So, yeah, we actually use it in both the width and the size. But then again, so does Raspberry.
Yeah, I'm just saying
Yeah.
error correcting code is very common.
Yeah,
It's common to use the use of it.
the use of it in the width argument. Okay, yeah, that's fair. Okay, so again, the high-level idea here is that now, if a proof wants to figure out what a row looks like, it has to query order log m variables. So it has to pay the price for the entire row, whatever we were paying before. And same for a column. That's just the high-level idea. And so quickly returning to the upper bound, we've changed the tautology now. So let's just make sure we haven't screwed ourselves over.
Yeah, but so what? Just a second. You're back to the upper bound.
Yeah, this is
upper
just-
bound is the same. Yeah.
Upper bound is the same. You just get some 6s in here. It becomes n to the 12. Nothing big. I just wanted to make sure because we have changed the tautology. So I just want everyone to see that. All right. Now, this is, of course, the lower bound that we need for the main technical lemma, which is that if the hitting set size is at least k squared, then the size of our proof, the smallest proof, should be at least n to the k. And we're going to use the usual 2 steps, which is you get width or degree lower bound. Degree is if you're in algebraic systems. And then you hit the thing with a random restriction and show that under the restriction you kill off all of the high width or high degree clauses, and then you get a contradiction. So, well, I thought I would have less time than I do, but we're just going to do a much simpler case, which is we're going to prove a height lower bound for tree res, in the same way that we just did a height upper bound for tree res. And then I'm not going to go into why this gives you the size lower bound, but it's pretty direct.
No, I meant it's not much simpler than the width bound.
Oh yeah, well, yeah. If I have time, which I guess I will now, I'll do the width. I'll do 2 or 3 words about the width bound for resolution, and you'll see it's almost exactly the same argument. But anyway, for now, let's just quickly do the height lower. So to get these height lower bounds,
So it's just a decision tree lower bound.
it's a decision tree lower bound. That's it. A decision tree lower bound. So what are we going to do? Well, we're going to play a game against potential proof pi that's trying to solve the search problem. Again, this is now a decision tree solving the search problem, so it's trying to find a violated clause. We're going to direct
It's basically trying to find the one.
the all ones column.
Or a 1-1.
Or it's trying to find a 1-1, exactly.
One in the both. In
M alpha and N beta, exactly. That's what it's going to try and find.
It's not done until it actually locates.
Yeah, and it has to know for sure that that's a 1-1.
So it's a one in
Yeah.
M alpha and M beta.
Exactly. So, yeah, and what we're going to do is we're going to lead it down a path where unless the path ends up being very long, it won't have found anything. So in particular, we're going to think of paths as a partial restriction to the variables of the tautology. This is pretty natural. This is right. This is what a path in a decision tree is actually, and I0 of the path is going to be.
Just a second. If the variables were actually not binary, but
Yeah.
you know, for values from M and from N.
Yeah.
And you looked at the decision tree for that.
Yeah.
Is it clear that you will need to query what, k of them?
Yes, you'd have to query k rows. Or k squared rows. So actually, yeah.
Yeah, k squared. That should be simpler to prove.
Yeah, the fact that you have to query
Or
k
you have to query the hitting set size.
hitting set size rows, exactly.
That's right.
And so the reason for this is that imagine you queried hitting set size -1 rows. Okay? So whatever rows you've queried, this doesn't form a hitting set. And now you claim that there's a violated clause in one of these that uses one of these rows. Well, you're going to pick a column as well. You're going to say that this column, whatever the hit set in the n beta is a set that's hit by these columns. Well, this isn't a hitting set, so I'm just going to pick a set that's not hit by this set. I'm just going to pick, you've picked less than this h size, so I'm just going to pick some set to assign to it that has that doesn't have any ones in there. It's going to be 0 everywhere inside that set. And if that doesn't exist, well, then it's a hitting set. So
The only tricky thing is that the decision tree can query the sets and the.
it can also query the sets, but because the sets are encoded by, well, once you switch back to the encoding, the sets are like log n variables per, so you can barely query any columns, right?
No, we are just working in terms of.
Oh, if you only get to,
K.
yeah.
You want to say, so why k squared actually? Why?
K squared is the, so k squared is the size of the,
Oh, sorry, k squared is the size.
Yeah,
You
yeah,
want to say you need to
Yeah.
query k squared.
exactly.
Right.
So you want to say that any decision tree that queries sets in one shot, as a column in one shot,
Hmm.
and rows in one shot, has to either query whatever case, what is it?
Well, I'm going to get to that in just,
But I thought you wanted it.
okay.
The bitwise version.
If you want the bitwise version, actually, these sets I0 and J0 you can think of as exactly querying an entire row or a column. So the I0 set is the set of all rows where you've queried at least log m literals from xi. And you can think of this
So this is
in
a
your unit.
reduction just using the encoding, the fact that you.
Yeah, exactly.
Yeah, so what you really need by this encoding, what you really need is to prove a k squared lower bound on the decision tree where
Well,
it's a large alphabet.
K squared on the number of rows or k on the number of columns. Remember, you also get columns, as Toni was saying.
Why?
So if-
is it k the number of columns?
Because you want a k log n lower bound on the height of the decision tree.
No, why is it true?
Because it's figuring out as n, which of course, so log n is much bigger than log n.
Yeah. So yeah, k log m is equal to log n. So if you want to prove,
No, forget it. Just
Oh, sorry.
I'm asking a general question. Doesn't matter the parameters. I mean, you have your A matrix, which is a universal set. That's what everything is based on.
yep,
And now there's a decision tree for the tautology, which is like an R-way. You know, it can ask row names or column names.
Yeah,
That's
exactly.
why- And you give all the bits. You know, we
Yep.
don't count.
Yep,
the
yep, yep.
integer.
Sure.
Yeah. So what is the low bound? The low bound says that the height is at least is a minimum of k squared columns or
Rows.
k rows.
K squared. So
k squared
yeah,
rows
k
or k columns.
exactly. K squared rows or k columns.
And why is this low bound? So you didn't. What's the argument that proves it?
Oh, so I mean, yeah, I'm about to do it in the binary case, but if you want the unit case, again,
It's much simpler. I mean,
So-
yeah.
okay, so the idea is, so the rows I kind of already argued. If you did it in one shot,
Yeah, but
then
you
if you
don't.
picked, yes, you don't. So here's the high level idea. Every time you pick a row or a column, let's say you pick a row, so you're going to query the identity of some row. I'm going to look at all the columns you know the identity of. And then I'm going to pick a row which is 0 in all of them. All right, so if you know this column, I'm going to make sure that whatever row I pick has a 0 in that column.
And why can you do?
Because you have at most k columns, and k is less than log m over 4. Now we use this symmetric thing. So if you have at most log m over 4 columns, I can pick a row that's all zeros in there. And now, on the other hand, and this is the easier one, if you pick a new column, then I'm just going to pick something that's 0 in all the rows you've seen so far because you don't have a hitting set.
Since k squared is actually less than log m over 4, we could have just used k squared earlier.
If you make k squared less than log m over 4, then this technique only goes up to cube root of log n instead of square root log n.
We don't have that anyway, so.
Yeah, that's true. We only have log n, so. But, I mean, I think I think it's fine. That's fine. OK, so maybe I don't, now that we've said this, I don't actually need to go.
Actually, no, you didn't finish. So you said what happens when somebody queries a row.
I already said when someone queries a column. Yeah. You pick a 0, you pick something that's 0 in all the rows you've queried because you haven't queried a full hitting set. Yeah. Sorry, that was the, I guess we kind of went over that earlier. But yeah, so this is the dynamic version. It's every time you pick a new row or column, you make sure it's all 0 there. And so now, even if you pick later, maybe you pick a column and it's got a 1 here, and later you pick a row that's got a, that's in that, that's where that 1 was. So it's not like the static system where I just make them all miss each other. But as long as I make this thing have a 0 there, there's going to be no issue. All right, now that we've said all this, I can probably skip very quickly through the next couple slides. This is just going to be the Boolean analog of this, which is if you have too few variables, I don't care what you do. You can take whichever assignment to it you want. As soon as you cross the threshold, so you know log m variables in column I, then I'm just going to pick a row that's 0 in all of this J0 thing, which is the columns we know about, which we can do because there are at most k of log m over 4 of them. And then I'm going to pick an assignment, an actual assignment to xi, so for all 6 log m variables, that's consistent with the path so far and gives me the row that I want, this row in the A matrix. And I can do this because I've fixed at most log m variables. This thing is surjective up to 2 log m. So I've got plenty of room to work with. And now I'm just going to remember this alpha I. And the next time that they ask me anything about row I, if it's already in I0, then I've already stored a value of alpha I for it. And so I'm just going to answer according to that. And this makes sure that we're going to end up in the place that I want it to. Yj, same thing. If you've got less than log n variables, I don't care what you do. As soon as you cross the log n threshold, I pick a set which misses all the rows we've queried so far. We know it exists because we haven't queried a full hitting set yet. I pick an assignment beta j, which is consistent with the path that gives me that set. And I store this thing, and from now on, I'll answer according to it. And I don't actually, I mean, we already showed that if you keep doing this, until you cross one of these 2 thresholds, you're never going to violate a clause. So if you claim a clause is violated, either it doesn't exist because there's a 0 there, or you've queried something outside of I0 or J0, at which point you don't even know the variables in it. So you're completely wrong. OK, so since I've got time, I'm going to give 2 sentences about how you change this to a width lower bound for resolution. And the simple argument, OK, so now instead of paths, we're going to have a res refutation pi, and we're going to argue that there's some clause d, so some line in the proof, such that I0 of d is at least k squared, or J0 of d is at least k. So similar argument to before. And to get this thing, there's this thing called a prover delayer game, which I'm not going to go into. But basically, think of it as the exact same adversarial argument we did before. But now the proof is allowed to forget the assignments to variables whenever it wants. It can forget them, and it's no longer charged for them. So this, in theory, could be bad for us because it could do this long chain and force us to say something bad, and then forget everything that it needed to get that bad literal, or that bad assignment, because it's already gotten its value from us. Of course, in our case, it's pretty easy to see that this can't help you at all, because, OK, if you forget variables, and you drop below the log m threshold, I'm just going to erase what I stored. I'm going to erase my stored alpha I, and then I'm just going to keep playing as normal. And now, to get a contradiction, I'm just going to say, like consider the last time that I was added to I0 or J was added to J0, then if I was added before J, or if I was added after J, then we know that we designed the row to miss J. And if J was added to J, if J was added after I, then we know that the column was designed to miss row I. So it doesn't really help that you can forget these things because, you get nothing.
Do you have examples where the width is small but the height is, where the width is W but the height is bigger? The height cannot be bigger than W log n. So why do we need to prove this even? I mean, if you have a size lower bound. The height lower bound gives the size lower bound, which gives the width.
The size lower bound, the height lower bound doesn't give a size lower bound, actually. We were cheating. Well, no, because imagine just a height H proof. For this tautology, I swept it under the rug, but
yeah, I know. It doesn't matter if you didn't show it, but you have it.
Yeah, we do have it because you got to branch arbitrarily on these things, which means the size is like 2 to the number of times we branched arbitrarily.
You get the tree size out.
Yeah. That's tree width. And now we're switching to res. This is not tree res anymore. This is resolution.
Yeah, but the width lower bound you can.
The width can be a lot smaller.
Yeah. Oh, right.
Yeah.
Sorry, good.
Yeah.
Very good. Yes.
Right. Yeah. In tree res, you're right. It doesn't. Yeah.
But if you had a resolution proof of width D,
Yep.
then you have a tree like resolution proof of width D, right?
Tree like resolution proof of width D.
What? Yeah.
Okay.
Right. You just use the same clauses.
Yeah, but
Oh, sure.
the height lower bound doesn't give you width lower bound.
Yes. Yes.
All I'm saying is.
Yeah, because you can use a dumb chain of inclusion, not x1 and then x1 or not x2 or x2 or not x3. And so this thing has height, however many variables I pick, but the width is like 2.
I think that's not the right example.
Oh, is that not?
Maybe the pebbling isn't better. I think the pebbling might go.
If you have a small width resolution proof, then you have a small, then you have a tree-like proof with the same
Width.
right?
Well, because you
And
just
this,
because you just can take the resolution proof and make
Yeah.
it a tree, but if the
Yeah.
size gets much bigger.
the size gets much bigger.
Right.
Yeah. But the height doesn't get bigger.
But the height could be a lot bigger than the
But
width.
the height in the resolution proof.
Yeah, that's what I was trying to illustrate with that example, where the height is like n.
I think
Okay,
that one
good.
actually
Yeah,
you
yeah,
can do
okay.
in log n.
Okay.
Touche. But the width is still constant. So
Anyways.
anyway, the point is for us doesn't matter. Exact same argument, but we tolerate them forgetting things with just one additional line. Okay. Now I promised a restriction argument. I'm going to give again just 2 sentences about this thing without any of the numbers. If you've got a proof that's too small, you're going to hit it with a random restriction that's going to set exactly log m variables per row and log n variables per column. And the variables it sets, it's going to set with equal probability 0 and 1. And you can show by the probabilistic method there's actually a lot of restrictions, a huge number of restrictions row that set every wide clause, wide as I0 is big or J0 is big, to 1. And now you can do the same wide clause lemma with the refutation restricted to this restriction row. And the reason you can do this is because the cutoffs for I0 and J0 were only log m and log n. This sets log m and log n. And in total, the surjectivity is 2 log m and 2 log n. So even if you restrict off log m variables and set log m variables during this argument, you're still surjective, and you can pick whichever row you want. And same for the. All right, and this is all the work you really need to do to get res. So what else? OK, this one we actually got to do. For null Sonnensatz and polynomial calculus, we do the same thing as Gillespie and Loria did for their version of Razvarov. This isn't the original reference. This is just the way that they did it. We do it the same, but actually we simplify it, or we think we simplified it a pretty significant amount, the argument. The core is the same. Okay, for res k, so resolution, res k is, so in resolution, the lines are all clauses. And the resolution rule says if you've got, maybe I'll go to the other board. Maybe I'll just use this board for this. So in resolution, we have clauses. And the resolution rule says A or X, B or not X implies A or B. So res k, that's a different k. I'm going to use r if no one minds. So res r. So now everything is, all the lines in the proof are r DNFs. So this thing is just an OR of a bunch of variables. This is an OR of ands of width r. And now what the resolution rule says is if you've got A or, these things are of width at most 1. So notice that this can be the same thing as res if there's just one variable down here. A or x1 or up to, say, xr. This is an OR. So these are all these are like all separate DNFs, essentially. And then you also have the clause B or, and then the and of the negations. So this is, let's say, x1 not and x2 not and up to not of xr. So this is one DNF. This is one term. Then you can derive A or B. So it's just an extension of the resolution rule to handle up to r variables for the r clauses. And so for this system, you kind of get an intermediate trade-off, which I didn't write on the chart, but I guess I can erase this now. I'll just write the actual result that we get. And this completely follows from the switching lemma that was proved by Buss and Pagliazzo and Segerland, which you can kind of switch a res R proof to a resolution proof. But you have to, the regime of parameters that they're working in is a little bit different than ours. So we had to play with things a little bit. But anyway, it follows pretty much directly. So if you've got res R, then the lower bound on automatizability you get is n to the O of log s over 2 to the r squared. This is your trade-off. So what does this mean? This means for res constant, you just get exactly what we had before, which is n to the little o of log s. And you get polynomial automatizability lower bounds for r up to, I think it's the square root of log. Let me just plug it in. So, and there's like a direct trade-off from this thing. OK, open problems. First off, we've done this for plenty of proof systems. If you want to do it for more, that would be great. We've been working on that first one for a couple months now. If you know anything about how to do that, I would love to hear it. Sum of squares is a bit weird. We don't actually know how to do this restriction trade-off. So we know how to hit Shirali-Adams with a restriction and blow up the size appropriately based on the degree lower bound. We don't know how to do it for sum of squares.
Since there are systems over wheels, you could even look at the obvious version where you don't glue lines.
That's true. Well, anyway. And then for cutting planes, if you assume the right lifting theorem, which is you have to lift to real communication, But I mean, if you get a constant size lift, then this follows immediately from the fact that we already have a decision tree lower bound. But maybe you could design a lifting theorem that doesn't work for all of Kringling's, because that would be a very nice theorem to prove a constant size lift. But if you could even get it for our tautology, where things are nice and regular, then maybe you could get some kind of result. And note that in the original, say, Aleknovich-Razborov results, you have a super polynomial lower bound on automatizability, which means you need a constant size lift in order to get, because basically the exponent blows up by whatever the size of your lift is. So if you don't get a constant lift, then you get no result whatsoever. However, in our case, you can go up to, say, log. The best known lifts are up to log right now, so you'd have to shave off another log factor. But there's the potential there. OK? As we observed earlier, up to k equals square root log n, which is dictated by this thing. If you get a better k, if your gap hitting set works for a higher k, then you get a better non-automatizability result, just right out of the book. And finally, this is a really interesting rigging up of everything, kind of forcing everything in the hitting set to count for log m, which just happens to work out to be the number you want it to be. But it's not crazy to think that there's a totally different technique to do this, working from some other gap problem and rigging things up in a different way. And in particular, if you can find one where the upper bound doesn't work for tree resolution. Here, our upper bound was like a decision tree. But if you can find one that doesn't work for tree res or null Stellensatz, then you actually have a hope of the technique extending past n to the log s. And in particular, who knows, sub-exponential is totally possible for resolution and other systems. But in particular, if it was resolution, that would be something we'd really care about. OK, thanks.